Now we're going to talk about linearly independent solutions. We have two key definitions. The first is that a fundamental set of solutions for an nth order differential equation is a set of n linearly independent solutions such that every solution to the differential equation can be written as a linear combination of functions from the fundamental set. In other words, if the set of functions y1, y2 through yn is a fundamental set of solutions for a differential equation, then the general solution is the set of all possible linear combinations of those functions, which means we have arbitrary constants multiplying in front of each function from the fundamental set, and that is how we generate our general solution. If you've taken linear algebra, the fundamental set of solutions is a basis for the space of solutions to the differential equation. This definition also refers to what are called linearly independent solutions. Again, unless you've taken linear algebra, you probably don't know what that means. A set of n objects, I'm calling them y1 through yn, they could be functions, they could be vectors, it could be anything, is linearly independent if the only way for a linear combination c1y1 plus c2y2 plus ... all the way through down to cnyn to equal 0 is if all the constants c1, c2, ... cn equals 0. So one way to think about that is that there's no way that these functions can cancel each other out in some way. There's no way to take, say, 4 of this one and 3 of another and 2 of the third one and have those cancel out. So they're all distinct. For us, since we'll be working with second order equations, if we only have 2 functions, they are linearly independent if neither is a constant multiple of the other. For example, x and 5x are not linearly independent, so we would say they are linearly dependent. Since 5x is just 5 times x, it's a constant multiple of x. But x and x squared are linearly independent because x squared is x times x, but it is not a constant multiple. Another way to think about that in terms of our actual definition would be if we had a combination of x and x squared that equaled 0 for all x. So when we say it equals 0, we don't just mean for specific values of x. We mean for all x. So we could use this triple equal sign to say it's constantly equal to 0. That could only be true if both c1 and c2 were equal to 0, because we know there's no way that just an x could cancel out an x squared. They're not like terms. There's no way they could combine to be 0. Now, while we will primarily be working with sets of just 2 functions, for the next example, let's look at a set with 3 functions. The set e to the negative 4t, e to the 0.5t, and 5e to the negative 4t minus e to the 0.5t is not linearly independent. It is linearly dependent. One way to see that is to realize that we can build our third function by taking 5 times our first function minus 1 times our second function. So the fact that we can build our third function out of the previous 2 functions means that this is a linearly dependent set. But if we want to think about this in terms of our definition of linearly independent and dependent, we would look at a linear combination of our 3 functions and say, can we make that equal to 0 without having to make all of the constants 0? In other words, can we choose c1, c2, and c3 such that these functions cancel each other out? And of course we can. We already sort of saw how to do it. So if we take 5 e to the negative 4t minus 1 e to the 0.5t, then that's exactly our third function. So if we just do minus 1 times our third function, then everything's going to cancel out. and we get 0, but we did it without having to have C1, C2, and C3 all be 0. So that shows that it's linearly dependent. So that's one way to check for linear independence. But there's another cool way to check linear independence of functions by calculating what is called the Wronskian of the functions. So the Wronskian of two functions, call them y1 and y2, is usually written W, and it is the determinant of the matrix formed by y1 and y2 in the first row and y1 prime, y2 prime in the second row. And if you haven't taken linear algebra and you're unfamiliar with determinants, this just means we take y1 times y2 prime minus y2 times y1 prime. If the Wronskian is 0, then the functions are linearly dependent. If the Wronskian is not 0, then the functions are linearly independent. Let's try it. Consider the differential equation 2y double prime plus 7y prime minus 4y equals 0, and show that the solutions y1 equals e to the negative 4t and y2 equals e to the 0.5t are linearly independent. We can show that they are linearly independent by calculating their Wronskian. So the Wronskian of these two functions is going to be the determinant of the matrix e to the negative 4t, e to the 0.5t, and then the second row is the derivatives. So the derivative of e to the negative 4t is negative 4 e to the negative 4t, and the derivative of e to the 0.5t is 0.5 e to the 0.5t. We're going to take that determinant. So we do e to the negative 4t times 0.5 e to the 0.5t, and then subtract e to the 0.5t times negative 4 e to the negative 4t. That is equal to 0.5 e to the negative 3.5t when we add the exponents, minus a negative 4, so plus 4 e to the negative 3.5t, and then combine like terms, 4.5 e to the negative 3.5t. And that's not equal to 0, so they are linearly independent.